So yesterday we went through the methodology for dark sirens. Like if you have binary black holes from which you observe gravitational wave events and you are not able to find any AM counterparts. It's not just binary black holes. Sometimes these binary neutron stars will also be like really far away and emit gravitational waves, and you may not be able to find the electromagnetic counterpart. So in this case, how to go about getting cosmological parameters out. And the main cosmological information that goes in okay, I forgot this. The main cosmological information that comes about from any of these analyses is related to a term called the redshift prior, because you can measure the distances of events based on the gravitational wave data, but you don't know the redshifts. And so how do you assign the redshifts? If you don't have a counterpart, then you need to have some sort of a prior along the direction to the gravitational wave event, where the redshift of the host galaxy of this event may be. And that is exactly where the cosmological information will go. So we spent a lot of time trying to understand this prior, go through some of the mathematics. One small thing, like while speaking, I said that by mistake, that this equality, there may be a proportionality, some terms may be missing, but it's not the case. So going from this term to this term is just conditional probability, because this is PA comma B. And then you take this PA given B times P of B. Right? So there are no proportionality terms which are missing. So I misspoke yesterday. So I just wanted to correct that before we move on. But the information about the cosmology is basically here, right? How do you connect the absolute magnitude to the apparent magnitude of galaxies? That's where the luminosity distance redshift relation goes. And so whenever you are changing any cosmology or any models for your any of these newer cosmological models that you want to try out, then you should be going and changing some of these. Okay. Okay. So then, so this was this redshift prior information. So P of Z given a direction in the sky and the cosmological parameters, etc. So it turns out to be this kind of a large equation. Okay? And one of the things that I was saying is, in principle, you also need to know what is the behavior of galaxies which are not seen at all. Okay, and so some time today we will spend on trying to understand what these missing galaxies are, how to characterize them, and again the uncertainties involved. There will be certain assumptions because you don't see them, so invariably you will do certain assumptions in order to understand what these galaxies are doing. Okay, so before we move to that, there are certain other technical aspects in GW Cosmo that I think it would be beneficial for you to know. Again, these are important in terms of the systematics, because there are uncertainties here which are also involved. So let me go through some of them. So when you look at the magnitudes of galaxies, so this is the absolute magnitude, or the something which is related to the direct luminosity of a galaxy, while this apparent magnitude is related to the flux of the galaxy. Right? So if you want to know the relation between them, you have to go through the luminosity distance. So this is well known and well understood. Here I'm putting luminosity distance in megaparsecs, and that's why there is a minus 25 around here. But in addition to this, there is this extra factor called K-core. Okay, so this is called the K corrections. So let's try to understand where these K corrections are coming from. If you had galaxies, all of them at the same redshift, then you would not have to worry about this. But because galaxies are present at different redshifts and you want to use all of them together in your analysis, you have to worry about this term. So where does this term come from? So this is a typical spectrum of an elliptical galaxy. You will see that there's a lot of flux in the redder bands, quite a reduced flux in the bluer bands. And then there is a characteristic feature here near 4000 angstrom. This is called a 4000 angstrom break. This happens due to a number of metal lines which are present in galaxies. So absorption features, calcium HNK in particular. So this kind of a drop, sudden drop in flux can also be used to figure out what the redshift of a galaxy is. Okay. Or if you see the entire spectrum, then you can see some of these lines, of course, and determine what the redshift of the galaxy is. Now let's consider two galaxies, one at this redshift, roughly redshift 0, and then another one which is at a higher redshift. Okay? So its spectrum will look like this. I have basically stretched by some factor the wavelengths. Because it is at a higher redshift, the entire spectrum is redshifted. Now, what's going to happen is when people carry out imaging surveys, they will have the telescope, there will be a camera in front of the in front of the focal plane, and then there will also be a filter that people typically put. So what this filter does is it removes the light from wavelengths other than where you want things to be. So for example, one of the filters could be just here, right? So let's suppose that it would block light which is outside of this wavelength region. Now imagine that these two galaxies had exactly the same spectrum, exactly the same luminosity. Now what happens is, in the redshift 0 galaxy, you are probing some different part of the spectrum. For the higher redshift galaxy, you are probing another part of the spectrum, because you see your filter will be calibrated to wavelengths today, right? And so it's the same exact galaxy. You see different apparent magnitudes for it, right? I mean, even different, if you account for the fact that you know the distance to these galaxies, luminosity distances, and then convert it into luminosity, just because you are sampling a different portion of the spectrum, you will infer a different luminosity for this galaxy. Okay? So this is the effect that these K corrections are trying to correct. The fact that when you observe a galaxy which is at a different redshift, you will sample a different part of the spectrum. So naturally the question then comes, so how do you do that? Because you have only observed this, right, wavelength. And so there is some sort of an extrapolation which will be involved, or understanding of how spectra of galaxies behave. Okay? One thing that can be done is, and this is what typically also happens, is instead of having a single band photometry for your galaxy, you have the photometry of galaxies in multiple bands. So it won't be observed only in this particular wavelength band, but another band here, another band here, another band here, and so on. So then in that case, you can piece together what the total spectrum of a galaxy is. Right? So in this case, if I had told you that, okay, I know the exact spectrum of the galaxy, now can you tell me what the K correction is? And that can be easily done, because what I will do is I will move this band corresponding to the rest frame these wavelengths, and then tell you what the flux coming from that galaxy is. But instead of having a spectrum, typically for most galaxies, you don't have a spectrum, just because they are too faint to observe with spectrographs. And so what you will do is you will observe in different bands and then collect these photons together. You can piece together a spectrum. And then based on that spectrum that you have pieced together, you can figure out what should be the rest frame flux that you will get for this galaxy at a higher redshift. Okay? And that is what this K correction does. So what this allows you to do is to put all of the galaxies on the same footing. Okay? In addition to these K corrections, there are also things called the evolutionary corrections. Okay, so even if you take a galaxy which is the exact counterpart of the galaxy that is there today, let's suppose two galaxies began exactly at the same time, and then one of them you're observing at an earlier redshift, one of them you're observing today. Then in between the time of redshift between that galaxy and today, the stars within that galaxy would have passively evolved. Okay? And so some of these stars, stars lose mass over time. They change in their luminosities. And so because of that kind of an evolution, there will also be a change in the luminosities. Okay. And so that is also something that you can account for. Okay, so that's called the evolutionary correction. I'm not showing you here. That's an additional term that you can put in. Why does just one point, and then I'll come back to you. One more point that I wanted to make is because so these things are important is because you are going to assign probabilities to galaxies based on the luminosities of these galaxies that they have, right? Probabilities to host gravitational wave events. And in that case, you cannot have galaxies which are similar just because they are slightly different redshifts to give them different weights based on the luminosities of these objects. Yeah. Yeah.
That is the passive, I mean, as for in Europe, like passive galaxy which doesn't create stars. So for those, like, are a sample based on that they have to have very less evolutionary counterpart, or like how they are sampled?
No, there will also be evolution. I mean, in fact, it is the evolution that is used in order to measure what the time is, right, between any of these different galaxies. So the cosmic chronometer data is based on the evolution properties itself, right, of these red galaxies.
So galaxies are sampled that which red galaxies doesn't create much of the stars or this is like sampling done by the
sampling. You mean sample selection? Yes. So sample selection for red galaxies will come to as well. But what you can do is you can verify based on the spectrum. So you look at the spectrum, typically if there is an ongoing star formation rate, then you can see certain emission lines in the spectra of these galaxies. And so those emission lines then act as tracers for the star formation. Okay. But typical elliptical galaxy spectrum, you will see basically red, the light coming from red stars. So these are really quite dead, old stars. And then they will also have these, like these calcium HNK features, you do not see like that prominently if you look at the blue galaxies, just because there is a lot of flux also in the blue. Yeah, so this is beyond the peculiar velocities right now. So you're going like really far away. Yeah. But in principle, yes, all the peculiar velocities will also have to be taken into account. Because it causes a shift to the spectrum, right? So there's no other way out of it. Okay, so this is about K corrections. So how do you actually estimate these K corrections? So as I said, you will have multi-band data. So multiple wavelengths, you will know what the flux is. And then after that, there's a nice paper by Blanton in 2007. What they have done is they've taken galaxies from the Sloan Digital Sky Survey. So hundreds of thousands of galaxies. They take these galaxies and then they make a PCA, so principal component analysis, to find basically what are the different kinds of types of galaxy spectra that you can get. Okay, and so you can see them here. Some of them are related to, like you can see all these emission lines, and then this basically is the spectrum of an elliptical galaxy and so on. So what they do is, given the fluxes measured in different optical wavelength bands, they will try to fit a combination of these PCA components with non-negative coefficients in front of them. Okay, so you'll say the observed flux should be reproduced within the error by some A times this plus B times this plus C times this, D, E, F, all these things, and then try to fit A, B, C, D, E, F, G to the fluxes that have been measured within the errors that are given. So once you do that, then you can reconstruct the spectrum of a galaxy. Once you have the spectrum of a galaxy, you can figure out what the K corrections are. So this there is a code which is available in order to perform these K corrections. It's called K correct, and that is also something which is widely used. So if you're interested again in some of these technical details, you can take a look. So how do these K corrections look like? This is shown for the B band, for example. You will see, depending upon the spectrum that you fit, these K corrections can be fairly flat, or it can change quite rapidly, right, with redshift. So this is redshift on the x-axis, and on the y-axis is the K correction. You change the spectrum, you will change these K corrections. No, so what you do is you fit the spectrum of a galaxy by looking at the broadband fluxes, by fitting A times this spectrum plus B times this spectrum and so on. And then you determine the values of A, B, C to reconstruct the spectrum of the galaxy. You reconstruct it. Once you have reconstructed, then you calculate the K correction. I mean, I think it will be equivalent if you did a K correction for this template, K correction for that, and then summed it over with the coefficients. It should be equivalent because it's a linear operation. So. Okay, so then what people do is also they simplify the computations of these K corrections. So if you look at GW Cosmo, for example, what they will do is based on one color and the magnitude of a galaxy, they can tell you what the K correction should look like. And the reason is as follows: if you roughly know what the apparent magnitude within a neighboring band is, and this particular band, you should be able to figure out how much of a difference it will make just because your galaxy has been redshifted. So initially, maybe only the nearby band is important, but as the redshift goes on increasing, then you will have to sample maybe another band and so on and so forth. So that it can tell you about the K corrections more and more accurately. Of course, that's not the most accurate way of doing it, but again, it's faster, right? Because if you want to do this kind of a fit and then calculate all the K corrections, it can take time. So instead of that, people then use colors. The other thing that can happen is if you look at galaxies, we will not know their exact redshifts necessarily. So people also have to infer the redshifts based on just the photometry of these galaxies. So these are called photometric redshifts. Okay, typically these photometric redshifts, they rely on the presence of these kind of features, right? So especially for red galaxies, these are pretty well measured. For bluer galaxies, it becomes difficult. It's kind of featureless spectra, so it is harder. But then if you have the photometric redshifts, you could estimate the K corrections based on these photometric redshifts. Because you need a redshift, right? If you don't know the redshift, you don't know how much to shift your wavelength band in order to get the rest frame flux. So again, other uncertainties, right, that are important to be taken into account. All of this can play a role in some manner or the other, start to impact your posteriors that you get out. Okay, then we will come to this question about the missing galaxy estimates. Okay, so the number of missing galaxies here, right? There are a number of them at any given redshift. This is because of the flux limit. This is something that this figure is something that we have been seeing quite often now. So what you can do is you can ask what is the incompleteness at a given redshift. Okay. So how will you estimate what the incompleteness is? The incompleteness, I'm not sure if I've written this correctly. It might be one. No, this is okay, I think. So the incompleteness is you take some minimum threshold up to the luminosity threshold here, okay, and then divide by the galaxies from this luminosity threshold up to here. Right? So that's the incompleteness. This is correct. And so what you need to do is there will be a function which tells you the number density of galaxies as a function of luminosity and redshift. This is called the luminosity function. Okay? So this number density of galaxies you integrate from L min to L threshold and ask how much of the galaxies are missing compared to if you had the entire range available. Okay? And you can compute what this incompleteness will be. At low redshifts, it will not be that incomplete. You will see basically all of your galaxies. And then as you go to higher and higher redshifts, you'll start to see lesser and lesser number of them. Then the question becomes, how do I define what this luminosity function is? Okay. So how much is the number density of galaxies as a function of luminosity? How should I calculate it? So as you know from this plot, fainter galaxies are only seen out to lower redshifts. More massive or more luminous galaxies are seen out to higher redshifts. So based on these kind of plots, you need to calculate what the luminosity function is. So how do you do that, right? So let's suppose I've given you galaxies from the Sloan Digital Sky Survey. I have given their apparent magnitudes. I have told you what their redshifts are. Okay, so these are spectroscopic redshifts. So you have established what the absolute magnitude is, or the total luminosity of a galaxy is. You have luminosity, you have redshift for each of the galaxies in your catalog. Now, how do you estimate the number density? Let's suppose you even know the cosmology. Okay. So how will you estimate the number density? It's basically number divided by volume, right? So in principle, you can count what is the number of galaxies within a certain luminosity bin and divide by the volume. What's the volume that you should use? Here, you are seeing galaxies from 0 to up to about 0.2 or so. Can you use that volume and divide the histogram? No, right? Because if you did that, then you are saying that you only see these many galaxies in the entire volume. And that won't be correct. And so you need to account for the fact that given your flux threshold, there is a limit of volume out to which you can see galaxies of a certain magnitude. And so there are different ways to do these kind of analysis. So people, the simplest way is to do something called a 1 over Vmax weighting. So what you do is, given the luminosity of the galaxy and the magnitude threshold that you have, so the limiting magnitude to which you can see galaxies, you estimate what is the redshift. Okay? And then you calculate the volume out to that redshift using the amount of area of the sky that you have covered and the minimum and the maximum redshifts that you use. Okay? So once you have that volume, then for every galaxy, you say that there is 1 over V. That is the weight that you assign, right? So in principle, let's say if you take galaxies which are just within this box, within the red box, okay, then it is easy. Then you can do the histogram and you can also do the volume, right? So that is not a problem if you have galaxies only in the red. But if you wanted also the luminosity function at faint ends, then maybe you can construct another box, and so on. So this method of 1 over Vmax, it actually kind of does that, okay? So what you do is you calculate the redshift max, as I said, and then compute the volume. And then instead of doing this, number of galaxies divided by volume, instead you do a count with 1 over Vmax. Okay? And this Vmax will be a function of L, right? Okay, so there is number of galaxies between L to L plus Dl. And this Vmax L to L plus Dl. So what this will do is, this will give you basically a luminosity function. You'll have to divide by dl in order to get the phi of L, for example. But this allows you then to get what the luminosity function looks like. Okay? Now what you can do is, if you assume that the luminosity function is not evolving as a function of redshift, okay, then you can fill in these missing galaxies. Right? So that is what is done in GW Cosmo and Icaro GW. So the assumption is, in the redshift ranges of interest that we will be looking at, that these missing galaxies will basically follow the same luminosity function as this entire population that you see here. So you use galaxies that you see at low redshifts to fill up the population, which is at higher redshifts. Okay. and then that allows you to estimate the incompleteness. It's an assumption, but needs to be tested. So you need to go to deeper and deeper surveys, try to check whether this holds or not in smaller and smaller redshift bins. And so that then allows you to figure out what the impact might be. Okay. Clear? Yeah. Yes.
Not the values of Fibonacci functions. Sometimes they quote just the upper limit and sometimes they quote just the lower limit. So can you tell in which context they quote what?
What do you mean by upper and lower limit of the luminosity function? The UV luminosity. Yes, yes, yes. Yeah, so the UV luminosity function is typically done at high redshifts. So once you see galaxies at high redshifts, then the fact that you have observed one galaxy already puts a limit that your UV luminosity function has to be above it, right? Yeah, and then the upper limits typically can come from, I mean, this I'm guessing now, is if you're looking at something like galaxy clusters, then areas around the galaxy clusters where the lensing can occur. And so you look at the region where the lensing has occurred, then um, there can be ranges because there are different lens models, which will tell you how much magnification should happen. And so that can give you a range, for example, for what the UV luminosity function looks like. So these are possibilities, and that's the reason why. I mean, it's quite uncertain, as you can imagine, because the further and further you go out, galaxies become fainter and fainter, and so getting the light from them becomes harder. There is another reason for why they may like tell you something which is an upper limit is if you know somehow that you have observed a field in which there is an overdensity of galaxies for some reason, then that can also give you an upper limit. And then ideally, whatever you have seen, it should be below it or something. So these kind of reasons, I mean, the lower limits are easy to understand, of course. Yeah. Well, I mean, ideally they would like to do these kind of things, but it's harder and harder, right? Yeah. And especially when you have galaxy clusters and you need to understand what the magnification around them is, that becomes trickier and trickier because like you have to understand what the gravitational lens modeling is actually doing. And so, yeah, becomes harder. This is much simpler at low redshifts because you have large area of the sky that you have surveyed fairly uniformly, as you can see here. Right? So then it's easier. Okay, so what do these luminosity functions look like? So this is dn by dm. So m is this magnitude again here. So this is in one of these bands, the BJ band. This is in the K band. And you can see what the luminosity function looks like. So if we use the galaxies that are actually in the catalog and try to compute this luminosity function, it goes like this and then it starts to fall off. So this is because of the magnitude threshold. At some point, you will start to taper off. You don't see all these galaxies. So you are missing all these galaxies here. As you go to lower redshifts, as you go to higher redshifts, then the magnitude threshold at which you cut off is even more luminous and more luminous and more luminous, and so on. But overall, you can see what the luminosity function looks like. So this is a determination by using this kind of a method, this thing, but in a small area of the sky. Okay, but what we care about in GW Cosmo or Icarus GW is over the entirety of the sky or within some pixels of what this luminosity function may be. And so that is this kind of reconstruction that you can see. So we need to account for all of this. Here is this BJ band luminosity function, and you can start to see sometimes there is some hum, sometimes there are missing galaxies, and so on and so forth. So whether this has to do with errors due to photometric redshifts or not, there's a lot of effort put in order to understand some of these systematics within the LVKs. So. Okay, so this behavior for the luminosity function, you can see that it looks like a power law at the faint end, and then it looks like an exponential drop-off as you go to the bright end, is something that you may also see from theory. Okay, so in theoretical models, it's very hard to predict the luminosity function, what it will look like. But if you run large simulations, large cosmological simulations with something like collisionless matter in them, then you can also plot the number density of halos as a function of mass. So dark matter halos as a function of mass. And they also have a very similar behavior, that more massive halos are exponentially less likely or lesser in number compared to the low mass halos, which show this kind of a power law behavior with mass. Okay. So the reason why there is a relation between the luminosity function that is seen here and the halo mass function is because galaxies live in dark matter halos. And there are scaling relations where more luminous galaxies, they are expected to live in more massive halos. Just because you have more dark matter, there will be more gas which pours in, you will form more galaxies or bigger galaxies. And so you expect there to be a scaling relation between the luminosity of a galaxy and the dark matter halo mass. And if that is the case, then you expect that the functional form that you had for the halo mass function will also be imprinted on the luminosity function of galaxies. So that's what you see. This kind of a functional form, which is power law at the end and then this exponential drop-off, this is typically fit by a function called a Schechter function. This particular function was proposed in the 1970s to describe how to explain the halo mass function that you get. Okay, and again, you can try to look at the derivation of what this Schechter function looks like, etc. It's present in my lecture notes. So if you want to go through it, it's under the title of Inhomogeneous Universe. So just take a look at it and you will see where exactly this power law and this exponential cutoff, etc. comes from. Okay. So that I will leave for the moment. So here are the plots. So based on these kind of luminosity functions, now you can estimate what is the probability for the host galaxy of your gravitational wave event given the redshift and the H naught, that this host galaxy is going to be in the catalog. Okay. So what you are seeing here is for K band, and this is for the BJ band, redshift on the x-axis. So the probability that your galaxy host will be seen in the catalog will be high if you are at low redshift, because you see most of the galaxies within the universe. But as you go further and further out, you only see the brighter end. And so your completeness will drop. Okay, so this is 1 minus the incompleteness, the completeness, that will start to drop. Okay. What are the different lines here? The different lines are telling you if you use only pixels where 10%, so this is 10% of the sky, where the magnitude threshold is quite deep. Okay, so you are seeing like really faint galaxies, but that happens only in very small region of the sky, just because there are deeper surveys in that area. So if you take that, then the completeness is expected to be high. And then as you go to brighter and brighter and brighter thresholds, then the completeness is expected to be low. Okay, so this kind of behavior you should be able to see, you should be able to understand why these things come. And you will realize that this probability that the galaxy is within the catalog, etc., this is a term that goes into the redshift prior, right? So this will be directly used when you compute the redshift priors. Okay. So what does this line of sight redshift prior look like? Now, if you take one particular pixel and you ask what my line of sight redshift prior looks like, then this is an example. So what you're seeing is overall the probability keeps on increasing towards higher redshift. just because there is more volume. So if you're looking at the same area in the sky, right, but then going further and further in redshifts, then you will see that it will form a cone. Right? So this kind of a light cone, okay, the same angle, theta. At this redshift, it's a smaller volume compared to at higher redshifts. Right? And so you expect that the number of galaxies that you get, the probability, the redshift prior will also increase as you go further and further out. Okay? So that's what you are seeing. But then there are these wiggles and bumps. And these wiggles and bumps are due to the large scale structure, right? So there will be some galaxies which are present here, maybe a galaxy group here, another galaxy here, and so on and so forth. And so that gives you the ups and downs in this line of sight redshift prior. And so now if you see an event in that direction, then there is a really good probability that maybe it is coming from this peak. And so this is where that Hubble constant information is going to come from. But you will use the entire line of sight redshift prior, not just one peak just because you saw that peak. Okay? So you try to marginalize over all these things, accounting for all this information, and then infer the cosmological parameters. One other important thing is this line of sight redshift prior, it does depend upon the resolution of your pixel. So do you take like a really large pixel or a small pixel? So this n side of 32 means that it is a bigger pixel, while 64 is 4 times smaller pixel. Okay. And so depending upon your resolution, you will see that you will either smooth out these overdensities, but if you go to higher resolution, then you can actually pick up these overdensities much better. You can think about it as if you had completely forgotten forgotten about the sky localization of your galaxies, you can compute over the entire sky, and then everything will just like completely smooth out to this uniform expectation that we have. So in fact, that brings me to the other part, which is we studied GW Cosmo in a framework where there are some galaxies and some part which is out of the catalog. But if you say that I don't give any catalog information at all, then it becomes something called the empty catalog run. And this empty catalog run will effectively turn out to be the spectral siren run, right? Where you only use the information about the mass distributions of your gravitational wave events in order to infer the cosmological parameters. So if you want to use GW Cosmo in order to run only the spectral siren analysis, then what you will do is you will do an empty catalog run. And so the line of sight redshift prior that you will give will have to reflect that empty catalog run. Okay? If you give a particular line of sight redshift prior in different pixels, then it will take into account the galaxy catalog. If you don't give it, if you give an empty line of sight redshift prior, then you're running the spectral siren analysis. So these things you should try out in the tutorials as well, because all of these functions exist. The only problem is that sometimes these spectral sirens and the galaxy catalog runs, they take a longer time. So it may not be instant gratification. It will take some time before these codes finish, and then you are able to plot those posteriors. Okay. So let me show you what the results from the LVK collaboration look like. So this is from the 2023 paper of the LVK collaboration. Here, what I'm trying to show you is that there is a sensitivity to the mass model that is adopted, right? So if you use a mass model, which is parameterized by a broken power law, so 2 power laws, or it's a power law plus a peak. So there's a power law, mass distribution plus a peak in middle with some Gaussian height and a scatter and so on, and the location for that peak. Then what do you get? And if you had a truncated power law, what do you get? And so on and so forth. So you have these different models, thankfully peaking roughly at the same location. Yeah. And then, but there is a slight variation on the accuracy with which you can determine. So the posteriors are a little bit broader if you consider the truncated power law compared to the power law plus peak. the more features that you have, it becomes easier to latch onto these features and to get the redshifts of the event. And that's the reason why you get a little bit better posteriors. But then the natural question is, which of these models should you trust? And that's the reason why you do nested sampling, which also gives you the evidence for your data, given the model. And so you should be able to then select between these different models using these Bayesian evidences. So please read about it, how to use evidences for carrying out model selection. And then that will help you understand how people like figure out in the presence of different hypotheses, which is the hypothesis that you should go with. So then yesterday there was a question about what happens if you have different event selection thresholds. So this is SNR greater than 10 events, SNR greater than 11, SNR greater than 12. So you try out all these different thresholds and ask how does your posterior change. So again, you can see some sensitivity, and this sensitivity also varies as you change the model. So all of these kind of systematic tests need to be done, right? So when you want to write a comprehensive paper, which accounts for all sorts of, not only the statistical errors, but also these kind of systematic errors, then you have to worry about this. So this brings me to another point, which is typically you want to perform these kind of analysis in a blind manner, okay? Which means that before you carry out the analysis, before you finish the analysis, you should not choose necessarily which are the threshold cuts that you are going to use. Okay. So you make sure that you decide what you want to do. You don't see what is the value of H0 that you are getting. And then you decide based on the systematic test that you have done, which is the baseline analysis that you will go with, okay, without seeing the answers. Okay. Otherwise, what will happen is, let's suppose you have some kind of a subconscious bias in your mind that the Rees et al. Result is correct. The low redshift supernova results are correct for the Hubble constant. Then you will keep on doing changes to your analysis until you get a peak at the right value. And then you stop there and then you publish that result, right? And that's not something that you want to do. And some of these things you may not like personally want to do it, but this sometimes happens subconsciously as well, these kind of choices. And so one has to guard against that. And so blind analysis is something that has to, I think until now, LVK is not doing a blind analysis. It does not matter really because the error bars are quite large for the moment. But once we start to push in the few percent regime, then I think this will become extremely important. Okay, so now that we have touched upon all of this, let me tell you the current issues with these current methods that are there. I've already alluded to you, but I wanted to put it on one of these slides. So you look at the spectral Siren method, which is the invariance of the mass distribution, which will then tell you the redshifts of this event. You can always ask the question, is the mass distribution of BBH events or any of these compact binary coalescence, is it expected to be invariant or not, right? I mean, who knows? And even if you put a small bit of a variation, then that can systematically alter your values. So what do you do about this? Is it something that is tenable in the future as you go to better and better precision or not? At least so far, you can hide behind the fact that we have tried to look for evolution. We have not seen any. But that does not mean that it does not exist. It's just that given your current error bars, you can't see it. But if you want to then go to better and better precision, we don't know what is going to happen. So one of the ways that this can be tested is you can make luminosity distance bins and then try to figure out whether the mass distribution here and the mass distribution here and there in the other bins, whether they look at least consistent or not, whether the shapes look consistent or not. There also you have to be a little bit careful because whatever bin in red DL you make, it will correspond to a slightly different bin in redshift. There is variation over redshift as to how many gravitational wave events you see. And so these things can skew your distributions too. So you need to account for all of that and ask whether the shape is actually going to change. So it's tricky. One has to put in a lot of effort to make sure that this is checked. Then if you look at galaxy catalogs, so you will say that, okay, let's forget our spectral sirens. I will just use the galaxies that I see in order to infer the Hubble constant by using the redshifts of these galaxies. The problem is these galaxy catalogs are very much incomplete. As you saw very quickly, like less than redshift 0.3, 0.4, you start to see a very quick drop in the completeness of these catalogs. And so if you see a drop, sorry. So if you see a drop, then it means that your galaxy catalog incompleteness is going to affect you. And as I told you, if you use a completely empty catalog, then you are back to the spectral siren method, where you are again having this problem. And so you need to have deeper and deeper galaxy catalogs. So how do you do that? Well, if you have an event, you go there, you try to carry out a deep survey of galaxies within that field. You try to follow up many, many of them and try to get galaxy catalogs which are more complete. That is one way. It's difficult, challenging, because there are now so many events. So basically that you have to carry out an all-sky survey, right? Because gravitational wave events, you are sensitive in all directions. So that's going to be hard. Obtaining spectroscopic redshifts, as I said, is also difficult because, see, imaging galaxies is easier because you have so many photons, you are collecting all these photons in a particular band. So you can observe the luminosity of the galaxy within that band. But now if you want to get a spectrum, you have to disperse all this light into the component wavelength locations, right? And so you have more limitations, like you take much longer time in order to get a spectra than to get an image, okay, of a galaxy. And so typically what that means is, given the finite amount of time that you have, you can image deeper, but you can only observe spectra of galaxies which are brighter. Okay? And so that was the case also for the Sloan Digital Sky Survey. It imaged quite deep, but the spectra were only up to a certain magnitude. Okay? And so this is just the things that you have to deal with. You cannot escape them. Then there is a question, do GW events really follow the luminosities of galaxies? This is not known, right? Is it really true that they are expected to follow the luminosities? This is an answer. In fact, there was a paper by Aditya Vijay Kumar, who was previously a student here, which showed that if you use these answers, that it follows the luminosities of galaxies, and then you predict what should be the redshift distribution of these gravitational wave events, then it is completely incompatible with what is assumed, right? And so there are all sorts of problems like this that you have to worry about. That it may not indeed follow the luminosities of galaxies, then what happens? In fact, you can show that, I think I had mentioned this as well, that if you assume that the probability that a galaxy hosts a GW event is completely independent of the luminosity, in that case, the limiting magnitude threshold that you use, this L-min value that is present when you infer the incompleteness, so this L-min value, this can be really, really low, right? And so your incompleteness will actually depend upon this L-min. Okay. What I've shown you is that the luminosity function, it increases as a power law as you go to the fainter end, which means in terms of number, the faint galaxies always dominate. And if the faint galaxies are dominating, then if you lower this threshold further and further down, then it means that your incompleteness will always come out very close to unity, right? Because whether you integrate from L-min to here or L-min to infinity, these galaxies will be very few in number, right? And so if that is the case, then the probability that the galaxy exists, the host galaxy of the gravitational wave exists in your catalog is basically zero. Okay? And if it is zero, then you are back to the spectral siren run and again the problems of the spectral siren method, right? And so there are real issues that you have to worry about. But if you look at the Schutz et al. 1986 paper, it seemed to talk about clustering of galaxies. It did not try to talk about host identification. It's written in a time when this idea about the clustering of galaxies, that you see the clustering of galaxies or the clustering of galaxy clusters, was starting to be known at that time for the first time, right? And because of that, the language that was used is slightly different from the modern language that we are now used to. But if you look at that paper carefully, it never tells you that you have to identify exactly the gravitational wave or the galaxy host for the gravitational wave event. Okay. In fact, it says that there should be galaxies which are clustered around these gravitational wave event. And so the question becomes, can we do a bit more with this information that galaxies are not completely randomly distributed, but that they are clustered with respect to each other? So that is in the next half an hour or so, I will try to go through these methods. So what is the clustering of galaxies? So you take a look at the galaxies. I had shown you this animation or a fly through the SDSS galaxies on the first day. So there are galaxies which are spread out all over the universe, but they are not completely randomly distributed. And when I say not randomly distributed, it means that the probability to see a galaxy at a particular location and then see another neighbor at a a distance, say, r away, it's not just Poisson distribution, okay? So if you have a galaxy here, then there is an excess probability over random that you will find a galaxy nearby to it, okay? This is called galaxy clustering. And this galaxy clustering has been measured in the nearby universe. So this is for galaxies with different magnitudes. So these are bright galaxies, these are faint galaxies. And you can measure something called the projected correlation function. This correlation function is exactly this excess probability over random to find galaxies separated by this distance. So you see that it is much more probable to find another galaxy nearby. And so that's why this clustering strength, it increases as you go to smaller and smaller separations between the galaxies. There's another trend that you see is that the fainter galaxies are less clustered compared to the brighter galaxies. Okay, so fainter galaxies, less clustering. As you go to brighter and brighter galaxies, you'll see more and more of this clustering. These are highly clustered. Within galaxy clusters, for example, you will see that many of them, you'll often find them fairly close by. This was done in luminosity bins. This is done in threshold bins. And again, you can see the same kind of effect. The reason why you see this effect is because, again, the fact that galaxies live in dark matter halos, and dark matter halos themselves are clustered with respect to the matter distribution. So this clustering of dark matter halos is something that you can also predict from simulations. And that's something that I can show. There is also a first principles way of understanding why this clustering occurs also in the first place. So you can try to take a look. Again, it's there in the notes. For lack of time, I will not go into it. Yeah. Yes. It's the clustering. There is structure in the universe. It's not just completely uniformly distributed. So all these spines and cosmic web that you see can be statistically characterized to first order with this clustering. Then there are higher order moments that you can also use, like the 3-point function, the 4-point function, and so on. No. You see it everywhere. This clustering is seen everywhere. In fact, the clustering is lower and lower as you go to higher and higher redshifts. Matter itself clusters, and the matter clustering grows as a function of time, just because gravity is attractive, right? And so inhomogeneities, they keep on increasing. And so this matter clustering itself, you can see, and the dark matter halos themselves, they borrow the clustering of matter, but then they are biased with respect to the matter clustering as well. Okay? So exactly what this power spectrum looks like, where the shape of this matter power spectrum comes, I encourage you to go through the notes. You will find most of it written there in those lecture notes. And if you have some doubts, just ask it on Slack. I will try to respond to the best of my ability. Okay, so good. So let's look at what this looks like. So this is a distribution in galaxies. This is from the Millennium simulation, some way of populating galaxies using some kind of semiotical methods. and this is the matter distribution in the simulation. So you can see that wherever there is an overdensity of galaxies, you also see that there is a corresponding overdensity of dark matter. Right? And so this delta M, which is the density of dark matter divided by the average density minus 1, that's this overdensity. These two densities are related. Okay, these two overdensities, delta G and delta M, they are related with a factor called a bias. Okay, it's not exactly the same. There is a bias factor. And so now if you take the power spectrum of galaxies, which is delta G, then that is related to delta M with a factor bias square. Instead, what you can do is you can also measure the gravitational lensing around these galaxies. Then that probes the galaxy matter clustering, and that gives you B times the matter power spectrum. Okay. So the question is, how can we use this fact that galaxies are clustered in order to get the redshifts of the gravitational wave events? So let's look at that kind of a picture. This is a crazy simulation that we did. Let's suppose in red, we are given fixed binary black hole events with unknown redshifts, okay? But similar kind of luminosity distances. Those are in red. And then in blue, what you are seeing are galaxy distributions. This is at redshift of 0.019, this is at 0.03, this is at 0.0461. Okay? So at different redshifts. What you will see is that the blue and the red, they are not much correlated here. They lie mostly on top of each other here. And then again, they are randomly distributed here. Right? That's because when I selected my gravitational wave events, they had luminosity distances corresponding to this bin. And because that was the case, my red points, which are the gravitational wave events, they have to trace the same large-scale structure as my galaxies. And so I will get a good correspondence, a good pattern match when I draw where the gravitational wave events lie and where the galaxies lie. Okay. Of course, I don't have so many gravitational wave events. Of course, my localizations are not so great. But you can take this idea in order to infer the redshifts of your events, of your gravitational wave events. Okay. So what you do is, you have the distribution of your gravitational wave events in the sky, some localization with large errors. You cross-correlate them with galaxies at different redshifts. So redshift bin 1, redshift bin 2, redshift bin 3, and so on and so forth. And you measure this cross-correlation amplitude. If the gravitational wave events lie at the same redshift as this sample, you will see a larger cross-correlation. If not, then you will see 0. So in this case, you are seeing 0, then a higher cross-correlation, and then almost 0 again. Okay? And so this peak will then allow you to figure out what the redshifts of those events are. That's the idea. Yeah. Right, indeed. So what you do is you bin galaxies, bin gravitational wave events according to a particular luminosity distance bin. And now you sweep through galaxies at different redshifts. Okay. So you have a galaxy catalog which spans a large redshift range. Then you can make smaller and smaller redshift bins. And then you cross-correlate your gravitational wave event within that luminosity distance bin with events here, with galaxies here, galaxies here, galaxies here, galaxies here, and so on and so forth. And then you measure this cross-correlation, you will see some peak somewhere that will tell you the redshifts. Okay? And of course, maybe what you will see is some of the events may be in this bin, some of the events in that bin. Then in that case, the cross-correlation will not be exactly 0 here. It will be a little bit more, then it will increase a little bit more here. And then. So that's what you will see if there is a distribution in redshift. So it depends upon how fine bins you are making and so on. So I'll show you in practice how this works, because we have done this kind of exercise in simulations. With data, it's still harder, and I will come to why as well. But this is the way to at least account for the problem that you don't have to rely then on spectral siren methods, and you don't have to rely on this problem of statistical host identification that everything becomes quite incomplete, right? And so your probabilities to host the galaxies are quite negligible then in that case. But you can see here that even if the host of the event is not in your catalog, the brighter galaxies that are there, they will still be clustered, right? Because they are still occupying the same kind of large-scale structure distribution. So you can imagine that I can only see the brighter objects. So if I see only the brighter objects, there will be fainter objects associated. You won't see them. That's fine. It doesn't matter. As long as you have some galaxies which are clustered with respect to the galaxy which acts as the host of your gravitational wave event, you are fine. Okay. So that's the beauty of this method. You don't have to worry about losing out galaxies or your host galaxy not being in the galaxy catalog. Of course, this will fail if you don't have any galaxy catalog support whatsoever. So let's suppose you go at redshift 1 or so, where you don't have galaxies at all, neither the bright ones nor the faint ones. Then of course this will not work because you cannot cross-correlate at all. Right? So you need to get some galaxies. If you have some of them, then you are fine, you are in business. So this is a thing that we did with Anthony Beira, who was a postdoc at IUCAA at that time in 2020. This is simulation. So we simulated about 50 to 500, 5,000 in this case, binary black hole mergers. You can see larger numbers. And then they were coming from the large scale structure distribution. So we had selected their host galaxies to be part of a dark matter halo within the numerical simulation. But what we did is we completely removed those halos from the simulation. So we only looked at the brighter masses, the heavier mass halos, and we carried out this exercise of measuring this cross correlation. And so you can see this was luminosity distance bin 200 to 400 megaparsec. In red, you are seeing the points that were measured for the cross correlation. You can see it's almost zero. There is some kind of a peak that you get. Then again, almost zero, some peak for the higher luminosity distance bin and higher luminosity distance and so on and so forth. Okay. And then we said, let's do, you can do a complicated model for this, but we did a simple model, tried to figure out where the peak of this distribution lies and what the error bar is. With what accuracy can you determine this peak? And then that gives you the redshift of these events. So you have the luminosity distance from the gravitational wave event, redshift from this kind of cross correlation measurement, and then you combine it, you can get the Hubble constant. So this is what you see here, luminosity distance here, redshift here. You can see the measurements of, so the error bars on the x-axis right now, there are also error bars on the y-axis. But since we are combining many, many events, the error bars will scale down as the number of events that you put in any given bin. So as you go further and further out, you can see those error bars at lower redshifts. It was less. And then you just fit a line that goes through this. This fitting of a line is also a little bit tricky because you have to not forget that there are error bars in both directions in this case. So the simple methods that you use to fit a line, they don't work. You cannot do, let me fit a line with the error bars on the x-axis ones, then on the y-axis ones, take some kind of bisector. That's not a principled way of doing it. There are Bayesian ways of doing it. Again, if you go to this paper, you will find how exactly we managed to do that. Okay, but you have to account for error bars in both directions, and then you can get a reasonably peaked posterior. This is 5,000 precision sources, so it takes a long time before you will get to this kind of an accuracy. But you don't need to have your host galaxy within your catalog. This is done purely with the bright galaxies that you can actually observe. The other method that we have been working on, so this is with Tathagat Ghosh, just recently that we published. Like if you take these kind of methods, you are doing it statistically, right? So you are making luminosity distance bins and then you are doing these cross correlations. Instead of that, we tried to ask can we try to estimate this cross correlation on an individual event basis, event by event basis? Okay. So what we do is the following. You can have a gravitational wave event which is located at certain region in the sky, let's suppose in that region. That's where at least the maximum posteriori probability is for the event to be localized. What you can do is you can count the number of galaxies within that region at different redshifts that are present. So let's suppose this is redshift bin Z min to Z max, some Z1, Z2. You count the number of galaxies that exist here. Then you shoot random lines of sight and you ask how many average number of galaxies that I expect, okay, within that redshift bin. Then you take a ratio of that. So the number of events, number of galaxies that you actually see towards the gravitational wave event in certain redshift bin divided by the expected number minus 1. So that is again an overdensity measure, right? So this delta is n divided by n bar minus 1, some kind of an overdensity measure. So this overdensity, I can measure it as a function of redshift towards the line of sight towards an event. So this galaxy overdensity as a function of redshift, you can actually model based on the number density of galaxies that you expect, what is the cross correlation between gravitational wave events and galaxies, and so on and so forth. So again, I would recommend you to go through that, through the paper to understand where this comes from. But once you can model this overdensity, you will see that there will be a Jacobian which takes you from the distances that you observed to the redshifts. So this term will be dependent upon the Hubble constant. And so your overdensity will be dependent upon the Hubble constant and what is the luminosity distance that is given by your event and where exactly you see these overdensities. So now you put many, many events together, you can compute a posterior on the Hubble constant as well. So this is similar to what the line of sight redshift prior would have done, but we are not doing statistical host identification. We are explicitly accounting for the clustering of these gravitational wave events with galaxies. So you need to have a model for this, so how to build it, etc. It's a complicated problem, but it can be done. Okay. Then you are away from the fact that you have to extrapolate what these galaxies in the faint end were doing, etc., etc. So this shows, for example, if you do random lines of sight towards all different locations, what are the kind of overdensities that you get? So this is overdensity distribution at low redshifts, then at higher and higher redshifts, this looks more and more Gaussian, right? And so you can estimate what this sigma is, and you can plot, this is a normalized distribution, delta divided by sigma. So there is some kind of non-Gaussianity, but this you can use in order to write down a likelihood for the observed overdensity given the modeled overdensity. Okay? And so once you have the likelihood, then you can figure out what the posterior is for the H0. So we have written a full Bayesian formalism. Again, more details are here. So this variance as well, you can compute how it goes as a function of redshift. You'll see larger variance at high redshifts and smaller variance at low redshift. The other way around. Higher variance at low redshift and larger, smaller variance at large redshifts. What am I doing? This is because there's more volume as you go to higher and higher redshifts. And so if there's more volume, then you expect there to be less of a variance because everything looks basically centered around 0, right? So you see this, if you sample larger and larger volumes, you are expected to see a distribution which is closer and closer to 0 and tighter in this particular space. So that's what you see. So you can take all this and build that model and compute what these Hubble constant posteriors are. So this is showing this posterior on the Hubble constant as a function of H0. This is showing using, if you had 150 events, 200 events, 250 events, what are the kind of constraints that you can get? Still not that tight, of course. You can see almost plus minus 20 here, right? So it takes a long time before we can reach like really percent level accuracy, but we can then be away from these assumptions that have been made. there are 3 different sets that we tried. So for example, if you had only 150 events, sometimes you can get these double posteriors as well. But as you go to larger and larger number of events, everything starts to converge. Okay, so this is because of fluctuations that may exist along the line of sight. So just random fluctuations. This is what is causing that. As you go to larger events, that goes away. In the different rows, what you are seeing is when I measure the over density, should I measure it really close to the gravitational wave event or really far away, right? So this is changing that cone, the angle of the cone in which I will measure the over density. This is theta max of 0.01 radian, 0.02, 0.03. And you can see that all of it converges to the same place, but the manner in which the convergence occurs can be different for these different theta maxes. So you can verify by making these different choices what happens, and to test the robustness of your result as well. Okay, so this was all in simulations. The reason why it has been difficult to try to reproduce this in observations is because you need to have uniform catalogs, galaxy catalogs in the entirety of the sky in order to carry out these cross correlations. We don't have uniform catalogs necessarily. This is one of the big surveys that is currently ongoing. The DESI, this is a spectroscopic instrument, is trying to take spectra over a large area of the sky. And what you can see is this is the locations in which they are trying to get all these spectra. This is in the northern side of the galactic plane. This is the southern side of the galactic plane. And what you are seeing are basically the imaging tiles. So you want to image the galaxies first before you target them for the spectra. And so these are how this imaging is done. Turns out that this imaging had to be done with a different telescope compared to this imaging, just because this lies a little bit further north. If you use a telescope in the south, you cannot reach these fields. So there was another survey which was done from the north. And then there was a survey from the south carried out with DCAM. And then you put it all together. When you put these things together, you have to worry about photometric offsets. So because the cameras that we'll use, the filters that you'll use, they'll not be exactly the same. There'll be small shifts. Even if you ask your vendor to make it to a certain specification, there will always be gaps. And then it can cause like millimag level differences in the photometry. If you observe the same galaxy using the 2 different telescopes, you will get 2 different values. So all these things can be calibrated using these common fields that you see here. Like there's a small strip which is commonly observed by both. So that is what is used to put this photometry on the same kind of 0 points. But then you use these galaxies that are present in order to make a galaxy catalog. Right now, the spectroscopic data is quite rare, quite sparse in these fields. So we have to use the photometric data itself. So how do you use the photometric data? So that's where these red galaxies, the luminous red galaxies that we are talking about, they come into the picture. The reason why these luminous red galaxies are good, because as I told you, the spectrum of these galaxies, that shows a sudden dip at about 4,000 angstroms. And so even if you have broadband fluxes, you can measure exactly from which band to another band, you're seeing the flux drop considerably. And by looking for this drop across the different bands, the drops and fluxes across these different bands, you can figure out what the redshift of this galaxy is. Okay? So the color of these galaxies in the color plane, you can try to select these luminous red galaxies by going to these different color diagrams. Okay, so the color is basically telling you the ratio between the fluxes at 2 different wavelengths. And so if there is a flux drop that you see, then you should be able to see it in the color plane. And so you can separate out galaxies from stars, for example, with these kind of color plots. And so these cuts are made in order to select these luminous red galaxies. And so what we did is we used this selection of luminous red galaxies and we tried to characterize what is the accuracy of their photometric redshifts. See, even after you get these galaxies out, you will have to characterize how well the photometric redshifts look like, right? Because photometric redshifts, after all, come from these broadband fluxes. They will never be as accurate as the spectroscopic redshifts. So how do you characterize this? You again use the same method that you use to characterize the gravitational wave events and get the redshifts. So this is some kind of a bootstrap. What you will do is you will use the spectroscopic galaxies to characterize your photometric galaxies, and then the photometric galaxies to characterize your gravitational wave events. Okay, so that's the idea. So we selected these photometric galaxies, and then we cross-correlated them with spectroscopic galaxies in these narrow redshift bins. And you can see again that you see a peak, and then zero cross-correlation, a peak, zero cross-correlation. This is real data now, not gravitational wave events, but photometric galaxies, right? And you can start to see these peaks. You can characterize the redshifts of the galaxies that you're going to use to cross-correlate with the gravitational wave events. So if you had not done any cuts whatsoever, this is showing what is the photometric redshift quoted, and this is the spectroscopic redshift quoted. Then you would see that for a given photometric redshift, there is a wide range in spectroscopic redshifts. If you use all of your galaxies. If instead you restrict yourself to the sample that we call luminous red galaxies, you see that this is much better behaved. Like whatever is the LRG redshift, the photometric redshift is very close to what the spectroscopic redshift is. There's still some leakage, but it's much less compared to what you see here. So this way you can characterize these things, and then you use these galaxies to get the redshifts of your gravitational wave events. There's one other thing that you can do, and this is the master's thesis of Devesh, who is also sitting here with you. What we are trying to do is to take galaxies that we observe. So this is again a familiar diagram, luminosities or absolute magnitudes of galaxies versus redshift, brighter galaxies here. You can see the green galaxies. These are the ones that you can observe, but the red galaxies are the ones which are completely missing, right? So then, is there a way to use this information again for these red galaxies, right? So we are trying to use the clustering information in order to get at gravitational wave events, which may be hosted by galaxies here. But there is another way of dealing with this problem. And that other way is as follows. What you can do is, you can use the overdensity of galaxies that you see here, the brighter objects that you see here, in order to fill up the galaxies that are there below. Okay? So how does that work? What I will do is, I will measure the delta bright of these bright galaxies in a given location of the sky. Okay? Now this delta bright and similarly delta missing, okay, which is n missing divided by n bar minus 1. These two quantities, they will be also tracing the same large scale structure, right? Because they are also coming from the same matter distribution that we have. And so they are also tracing the large scale structure. These two will not be exactly the same. There will be a ratio of biases between them, but that's okay. You can try to estimate that ratio of biases and fill in the galaxies that you expect there to be missing in this region. If you do that, then you have automatically populated galaxies which are missing. And so hopefully the host of your gravitational wave event will also come out to be in that location. And so you can fill all these missing galaxies in your survey. And now you can run the statistical host identification technique, because now that out of catalog term will not contribute anymore, because you have filled up all your galaxies. Your survey, your galaxy catalog is not incomplete. Okay. So there are of course assumptions related to what is the ratio of these biases. You can try to estimate that ratio based on galaxies that you observe in the nearby universe. But this is a plausible way, again, to fill up these galaxies. Yes? Yeah, so see, these are faint galaxies. These are brighter galaxies. I told you that brighter galaxies are more clustered than fainter galaxies. So they have a higher bias. And the reason why it, again, works is because brighter galaxies live in more massive halos, and more massive halos are more clustered. Yeah. Okay, so this bias is also funny because it's something that can be also easily understood. So one of the common examples that I give is that if you look at the Earth itself, and if you try to find out where are the highest peaks on the Earth, right? And you'll see, the highest peak is Mount Everest, but then there are many, many peaks which are just lying nearby, right? So K2 and others, which are lying really in the neighborhood of these highest peaks. So similarly, once you are over with the Himalayan range, then we'll go to some other range, and then there will be a highest peak there. And then again, you will start to see many, many peaks just lying nearby, right? And so even though these peaks are coming from the variations of the Earth's surface, right? The deltas that you will get for over the entire Earth's surface compared to the deltas of the peaks themselves, you will see that the deltas of the peaks are much more concentrated in certain regions. They are not exactly following the overdensity of the total peaks that you see on the Earth. Okay? And this happens because, see, if you are on a large scale fluctuation, then it is very easy for you to become one of these highest peaks, right? Even if you put like one pole here, then it becomes higher, right? And so, like making small fluctuations on top of large fluctuations which are already present can really quickly give rise to many, many peaks. And so this gives rise to this bias. And now, because more massive halos are more biased, more luminous galaxies are living in them. And so they are more clustered with respect to the entire matter distribution. And so you get this, you have to account for this ratio. You put in that ratio. You need to know what is the expected number of these galaxies. So again, you use galaxies at lower redshift to figure out how much number density should be here. But most importantly, you use the large scale clustering information of this brighter end in order to fill up these galaxies. And once you do that, then hopefully you can recover this missing information and be less sensitive to all these cuts and all these assumptions that go into either GW Cosmo or Icaro GW. Okay. Then finally, in the last few minutes, I also wanted to highlight some work here, which is also very interesting in order to use gravitational waves in order to do cosmology. So the idea was to use the gravitational waves which are gravitationally lensed. Okay, so gravitational lensing is this effect where the light coming from background objects, if there is a foreground mass distribution in front of it, along the line of sight towards this object, then the light coming from these directions, it can get bent and arrive at you from different directions. Okay, so instead of having just one single geodesic that light takes, it can take multiple different paths and also arrive towards you. And so what this means is that you will see copies of the same image. So this is very famously seen in the electromagnetic domain where you see quasars. So the same quasar which is being multiply lensed. So you see 4 different images of the same quasar. Then another thing that happens because of this lensing is that the ray of light which comes from one direction compared to the ray of light which comes from the other direction, they typically don't undergo the same geometric path length. Okay, and so there will be a time delay between the time that it takes for the ray from one direction to come towards you and the ray from another direction to come towards you. Okay? So this time delay can tell you something about the potential as well, the dark matter potential or the matter potential which is causing the lensing. Okay. In addition to the geometric path, there is also something called the difference due to something called the Shapiro delay. So as you go closer and closer to massive objects, you will see that the speed of light as inferred by you, it will slow down. And so some of these light rays which will go a little bit closer to the mass distribution, some will come from further away. And so that also introduces a time delay. So the total time delay that you see will be a combination of these effects. Okay? But this time delay itself is related to the redshifts of the events, to the redshift to the lens and to the source as well. And it is also proportional to h naught, the Hubble constant, because any time that you take in the universe or any distance scales, they are also proportional to 1 over h naught. And so there is cosmological information in these time delays. So what you can do is, in the future, when we will observe gravitationally lensed gravitational wave events, then you can try to make a distribution of the time delays of these gravitational wave events. Remember, gravitational wave events, they happen very quickly. So there's like the CBC merger, within a few 100 milliseconds or so, you'll start to see it, right? And then it disappears. So it's a very transient event that you see. What this means is that you can really accurately measure the time delays of these events. Okay. So even though you cannot localize it that well, if two events are coming from different directions and are corresponding to the same lensed event, then you should be able to measure the time delays really precisely. So you can make this distribution. You can take the observed number of events at a given delta Ti and so on, and ask what are the cosmological parameters which will give rise to this. So again, there's a Bayesian formalism against it. You can see this paper with Souvik. Ajith was the second author on this, and how to get cosmological constraints out of this. So this is also another method that you can use in order to do the cosmography. You can see this h naught versus omega m, and indeed you can get good constraints. There are of course different bells and whistles that you can play around with in order to establish the robustness of your results. And then this is what Planck has given you. And so you can compare the two. You can use the two in order to use them as complementary probes and get better constraints and so on and so forth. Okay. So this is also another, this is not from real data right now, simulations, of course. Yeah. So right now we have not observed gravitationally lensed gravitational wave events, even though the search is on. Okay, and in fact, there are multiple algorithms that were written together. Many people from here, especially Ajith's group, has been leading some of this work. It is very hard to find these gravitational wave events, and so let me tell you why. Maybe that I can take the next couple of minutes for that. See, what you get from LIGO are these triggers, right? And so you will see a gravitational wave event, and then you will see another gravitational wave event. So you will get the localizations for each of these events. And so what will happen is you will have to see whether these localizations are actually corresponding to the same area in the sky or not, right? If they correspond to the same area in the sky, then you are likely that, okay, maybe this gravitational wave event is lensed. Then there are certain time delays which make it more likely that it will be lensed than not. Right? So if these time delays are separated by a large amount, then who knows? But if they are separated by a small amount and then you see it, then maybe there's more likelihood that the sky areas also overlap. The mass estimates that you get, etc., whether they overlap or not, that is also something that you need to see. And so it's complicated, right? The distance estimates that you will get will actually not match, okay, from these events. So the m times 1 plus z will match, but the distance estimate will not match because the amplitude will be affected by the magnification that happens due to the lensing. Okay. So you have to take into account all these things to build a Bayesian, again, evidence whether two gravitational wave events that you see are really lensed or they are just completely unrelated. And so, again, tricky thing, people are trying to work hard in order to find these gravitationally lensed events. And hopefully in the near future, we'll detect the first events. And once that is done, then once you go to more advanced detectors, then hopefully you will see many, many more of these events. And so that will allow you to put these kind of constraints on cosmological parameters as well. Okay. Yeah? Yeah.
When, like, from the moment we start detecting them, do you think we access larger redshifts?
Yeah, in principle, magnification always allows you to access larger redshifts, right? So even fainter signals you should be able to see. But then there is also a finite optical depth, right? And so you need to worry about what is the optical depth, how many sources are going to be there, at higher redshifts and so on. So it's a complicated combination of all of these as to how much change it will make. But exactly this magnification effect is being used to estimate the luminosity function, the UV luminosity function at high redshifts, as was mentioned before. Yeah. Oh, no, no. So fainter galaxies at higher redshifts, you will only access towards regions which have higher magnifications. But there's very small region in the sky which gets magnified because of gravitational lensing. So you cannot rely on, in fact, most of the galaxies that you see are demagnified. So if you look at the average lensing effect, most of them will be demagnified. Only a certain region will be magnified. On average, it is unity, because from everywhere in the sky, you should not see any magnification whatsoever when averaged over the entirety of the sky. But most directions, they travel through voids. And so you see demagnification. And then there is small regions in the sky, small pockets, which we will see magnified. Yeah. Okay, so let me come to the last slide. This was something that we began with. Wanted to know how old is the universe, what is it made up of, and so on and so forth. I told you that you can use distance measurements as a function of redshift, at least, to answer maybe the first question, because you get the Hubble constant. If you take inverse of the Hubble constant, that gives you a time scale, and that time scale sets the age of the universe, basically. It also sets the length scales of the universe. What is it made up of? You can use these distance measurements as a function of redshift to figure out what are the constituents of the universe. So this was famously done with type 1a supernovae and is being done with baryon acoustic oscillations as well. We saw how gravitational wave events can contribute to it, okay, and contribute to learning about some of these things. This one, further out, early universe, what gravitational waves can do for you. That is something that I hope you are learning in the other classes which are going on. And this fate of the universe, it ties down to basically what the dark energy is doing, what is its equation of state. Again, these distance measurements as a function of redshift can help you to do that. So I hope we have come back to a whole circle. We started with these big questions and how we can address this with gravitational wave events. Details are murky, but that's what these kind of advanced schools are for you to learn what these details are, and then you can go back and hopefully chisel, work hard on some of these smaller and smaller problems, and then we can build a community which can actually exploit all this data that we are going to. So with that, I will stop here.